Okay, welcome to the second TA session of Design of Steel Structures taught by Professor Damodar Maiti. I am Trisha Chakraborty, one of the course teaching assistants. I am a PhD student at the Indian Institute of Science, Bangalore. We'll start by a quick recap of what we went over last week. There are two broad branches of structural engineering: analysis and design. Analysis is the forward problem where we are given the structural dimensions, the boundary conditions, and the applied loads, and we want to find the response that is going to be induced in the structure, that is, the forces, deflections, the stresses, strains, and all that. And design is the inverse problem, that is, we have the load that we want the structure to withstand, and we have certain criteria on maximum deflection or stress. We know the criteria of stress because we know what material we are going to be using, and we know the yield stress of that material, be it steel, be it concrete, and we have to find the optimal size of the structural elements and how we are going to arrange the elements, what kind of boundary conditions we are going to use. So we are the design is what we basically, as practical civil engineers, design is what we do to build structures, buildings, bridges, etc. And last semester you must have done in your third year a course on design of concrete structure, reinforced concrete structures, RCC. And now this, since this course we are looking at the design of steel structures, it is important to see why, what are the advantages of steel over concrete, because concrete is the most versatile material for constructions. So steel is much stronger than the conventional concrete. That means its compressive strength, its tensile strength is much higher than concrete. It has a very high strength to weight ratio, that is, to make a steel element, structural element, or a concrete structural element both withstand the same load. If we are to make that, the concrete section will be much wider and it will be much heavier. So steel structures are generally lightweight, and steel is ductile compared to concrete. That is, it, we saw the stress strain curve, which we will go over again. Steel deforms, allows a lot of strain to develop in the material before it actually fails. So even if it is about to fail, it will give ample warning time for people to evacuate or to take action, or maybe even repair work. If we see steel is going to show a lot of deformation before it fails, so if a certain deformation limit is crossed, we will understand that this part needs to be repaired and we can address it in time, unlike concrete, which is relatively brittle, so it will give less warning time and it may cause more damage in the long run. However, steel is much costlier than concrete, so steel design is a critical subject. And why do we need design? Design, this term, what exactly it means: the components individually and the entire structure should withstand the load throughout its lifespan, satisfying serviceability criteria. Now, withstand the load. What is this load? This load is what we are designing the structure against. There are four broad categories of load. The common ones, that is dead load, live load, wind load, and earthquake load. Dead load is the self weight of the structure, of the floor finish, like the marble or tiles. That is the dead load. The live load is everything else, every other vertical force that we are going to put on the structure, like the load of furniture. Sometimes furniture is confused to be dead load because it is an inanimate object, but furniture is also live load, because only the self weight of the structure. Only the self weight of the structure and the floor finish is a dead load. The live load is every all other full loads that we are going to apply on the floors, the furniture, people, or whatever. And for in the case of bridges, the vehicle loads are live loads, and wind load and earthquake load are lateral loads. they come in the horizontal direction. In the two perpendicular direction, we consider them. Earthquake load, what we design a structure, what earthquake load we design a structure against depends on where we are constructing that structure. So the Indian code divides the mainland of India into certain earthquake zones, zone 1 to 5, where 5 is the most severe, and 1 is the least severe. So we have formulas to calculate the earthquake load. And wind load mostly depends, it also depends on the area, but there's a basic wind speed given for all cities of India in Indian codes, and it also depends on the height of the structure. As we go higher, the wind load is supposed to be more. Then there are some other kind of loads like snow loads, etc., that we have to consider for certain structures, or wave loads in offshore structures. This is the load part. Then throughout its lifespan, there's a lifespan. Every structure, when we are designing it, we have to specify a particular lifespan that we are designing it for. It is generally 50, 60 years or something of that sort before it will need major repair, and after that there will be an ultimate lifespan. So for bridges or for residential buildings it's generally 50, 60 years. For institutional buildings like college campuses, school campuses, it is generally more, 100 years or something. And serviceability criteria, this withstand the load throughout its lifespan. This is to do with the collapse criteria. Collapse criteria means that withstanding the load means a structure should not collapse. And there is another criteria, that is the serviceability criteria. It has to do with deflection. The collapse criteria has to do with forces or stresses, because when a structure or a material fails, it fails or breaks because the stress in the structure, developed in the structure, exceeds its fracture stress that it can take. And serviceability criteria has to do with deflection or strains that that varies very broadly from structure to structure and depends on its purpose. For example, in factories, as I said last time, in metal work factories, there are mechanisms that need certain amount of headroom clearance. Or in a, suppose in a mall basement parking, you are, when the car is to come out, or a truck is going to come out of a ramp, then when it is coming out, there is an amount of headroom clearance that is needed for the vehicle to pass through. So that if the beam above or the slab above deflects beyond a certain limit, it might hamper the purpose for it was built. So that is a serviceability criteria. So that also has to be satisfied, that it is possible that a beam does not fail, does not actually break down, but it deflects so much that it is not serving the purpose. So that is called failure in serviceability criteria. So for design, we have to make sure that both the collapse criteria and the serviceability criteria are satisfied. Fully design a structure. To properly design a structure, we have to ensure that it is economical to construct it without compromising safety. This is also very important because we cannot keep increasing the safety to an infinite level. Infinite doesn't exist, but whenever you are, whatever building, whatever structure you see around you, it was always possible to make it safer. Like when you see the beams or columns in the room you are sitting in, there is some amount of steel reinforcement inside the concrete. It could have been more, right? Then it would be safer, and like that it could always be safer. But we cannot keep on making that. We have to draw the line somewhere, because as we make it safer, the cost of construction is also going to increase. So we have to strike a balance between the two, and that is the the art of doing that is called making a cost effective design. And for that we need to know the design procedure in detail. Now we just briefly go over the mechanical properties of steel that we discussed last class. The physical properties of structural steel as detailed by this clause of IS 800 207. This is the Indian standard code for steel design, irrespective of its grade. That is, we know there are several kind of steels, fe 500, fe 415, etc. But certain properties, five properties, we can just take irrespective of its grade: the unit mass or the density, the modulus of elasticity, which we also call the Young's modulus, is denoted by E. It's 2 into 200, 200 gigapascal. This is 2 into 10 to the power 5 megapascal. The Poisson's ratio mu is zero point 0.3. The modulus of rigidity is this, and the coefficient of thermal expansion alpha is 12 into 10 to the power minus 6 per degree centigrade. This is also important in steel and not so much in concrete. In design of RC structures, you probably have not come across any design criteria that has to do with the temperature variation, but in steel it is important because steel has a much higher coefficient of thermal expansion. And the main the properties that we are concerned about, that is not common across all grades. Okay, this is these five properties. The code says that these five properties you can take whatever the grade of steel be, but this these two, yield stress Fy and ultimate stress Fu, vary from grade of steel to grade of steel. And these are the roll steel structures, the roll steel sections that the BIS shows. It has tables of weight per unit length, geometric dimensions, and other dimensions for various types of steel structures. This is an IE section, also called a joist. This is a channel section, an angle and T sections, and there are several hollow and solid sections. These bars are solid sections, flats, plates, or strips, and these are hollow sections, square, rectangle, circular. And this elasticity curve is again very important, as we discussed last class. This stress versus strain, the elasticity curve is obtained by applying by performing a tensile stress on a bar of steel. The load is increased, the load pulling it is increased gradually, and the load is noted down and its elongation is noted down. And stress, we know, is of the applied force by area. So P by A is the stress that we are going to plot on the y-axis, and the strain is the elongation that we note, that we observe, divided by the length of the specimen. So that is the strain that we are going to plot on the x-axis. There are certain important points in this curve. Like, we will see that up to A, the curve is a linear one. So A is the limit of proportionality, the point where the linear nature of the stress strain curve graph ceases. And the slope of this line is a Young's modulus, because when the Hooke's law is followed up to A, uh, stress is proportional to strain. So sigma is proportional to strain, and the constant of proportionality is E, the Young's modulus. So the slope of this curve is stress by strain, that is Young's modulus. Then up to B is the elastic limit. It means that the limiting point for the condition that the material behaves elastically. But Hooke's law does not apply. Hooke's law means stress is proportional to strain, but this part, this A to B part, is not linear. Okay, this is non-linear, so Hooke's law is not applying, but the material is behaving elastically. What does that mean? That means that beyond elastic limit there will be some permanent deformation or permanent set when the load is removed. But up to B, when you apply a certain load, that up for B there is a corresponding load, right? B has a corresponding stress, and if you multiply that by area, you will get a load P. So till you apply that magnitude of load, if you remove the load completely, the specimen will go back to its original configuration, that is, it will regain its original length. But beyond C, the material starts behaving inelastically. That is, so even if you remove the load entirely, there will be some residual deformation remaining, that we call as a permanent set. And C and D are the upper yield point and the lower yield point, points after which strain increases without corresponding high increase in load or stress. C and D are sometimes taken as the same point, because yield stress we just take, like we saw here, yield stress is Fy. It is generally one single value. In Fe 415 that we use, Fy is 250 megapascal. So after that, beyond C or D, we'll see that the material starts to kind of flow. It is called flowing because the strain is increasing a lot and the stress correspondingly increase very less. There is a distinct difference in the slope of this part and this part. So these are the yield points. We see the material has yielded, and we would prefer not to load the material beyond its yield point. And E is the ultimate or maximum tensile strength point when necking starts. Necking means this part is necking, where the cross section reduces considerably in magnitude. So, and E is also the topmost point in this curve. So it is the highest stress that the structure can take, and after that the stress falls again. The even if strain is increasing, stress is falling. And F is the fracture point, where it is the point where the material breaks. So the stress corresponding to F, the stress here corresponding to F, is the ultimate tensile strength Fu, a stress Fu, that is 410 in the steel that we use in India, 410 megapascal. Now we look at the purpose of this class is, last class we look at the material, steel as a material basically, and today we look at the design principles that we have to follow. So first we have to look at the modes of failure in a beam. while we were doing concrete structures, design of concrete structures, what did we basically do? We To design a beam, we there were two criteria: bending and shear. They were the only criteria we were designing it against. Basically, we tried. Made the section. We give them. I mean, fix the dimensions of the section, and we took the percentage of steel reinforcement based on the bending moment that we want to design it against, the factored bending moment, and then we checked if the section is enough to take the shear, or if and we designed stirrups for taking the shear. So that is what we were doing against bending and shear. Now in steel structures there are certain strange or different kind of failure modes. Bending is, of course, bending is very intuitive and you have already learned. Gravity load gives rise to bending of a beam. What are the gravity loads? The dead loads and live loads, which act vertically downwards. Wind, earthquake loads act in a horizontal direction, so they are not included under gravity loads. The gravity loading gives rise to bending of beam. It causes longitudinal stress to be developed in the beam. Longitudinal means along the length of the beam, and transverse beam means perpendicular to the beam. This is the beam axis. Longitudinal means along the beam. As the bending moment increases, flexure is another word for bending. So as the bending moment increases, the flexural stresses increase further till they reach the yield stress. At a certain point, either the steel yields in tension or yields in compression. It depends on which side it's where. When we are applying a gravity load like this, the beam is bending like this, we can see that compression is developing on the top fibers, and tension is developing in the bottom fibers. This behavior remains the same whatever the material is. It is understandable intuitively that if you take a copy or something, and if you apply a load on one side, you'll see it bends in this way, and you'll see that the top layer of the topmost sheet is compressing and the bottommost sheet is elongating. So at a certain point, the steel will yield in tension or yield in compression. What does that mean? That means that the developed compressive stress or the developed tensile stress has reached or exceeded the yield stress of the material. That is the Fy. At this stage of loading, the beam section becomes plastic, fails by formation of a plastic hinge at the location of maximum movement being induced by loading. This part we actually don't wait till this much. We try to keep it under the yielding only. And plasticity, we can see what plastic means. That once it has yielded, this zone is called partially plastic. This zone is called elastic up to yield stress, and beyond yield stress we call it partially plastic. So once the yield stress has been exceeded in the material, the developed yield stress has exceeded the yield strength of the material, it becomes plastic. And then a plastic hinge develops. It is an idealization, basically, that wherever along the length of the beam, where at whichever point the bending moment is maximum, a plastic hinge develops. And according to that, we have to make the design, but we don't go into that much detail in steel design. See, basically, the material can be studied in great detail up to its failure, but laymen, when they're designing a steel structure, they are not supposed to know the all the details of the behavior of the structure. They have to be given a very simple set of rules to follow. Like, so if you see IS 800, which is the which is a design code for steel, you'll see it is just mentioned in step form. Even in the RCC code IS 456, it was mentioned in stepwise. Just check this criteria. If it passes, uh, go to this step. Otherwise, do this, and like that. But there you won't see the details of the behavior of the structure. That this is how the structure is going to behave. Here, the below yield, the F when F is the developed stress and Fi is the yield strength. So till F is less than Fi, this is below yield. Then it yields when they are two are equal, and when it becomes plastic, like this, the in this zone the Fi is greater than the F. So it okay, this diagram is a little unclear to me right now, but it is not generally used in design. I'll have to look back to it. And when it is fully plastic, this axis, okay, this point is a neutral axis point. The neutral axis, you know that during bending, neutral axis is the axis where there is no tension, or where no tension or no compression develops. So basically, if the gravity load is downwards and the beam is bending like this, the top is under compression and the bottom is under tension. So the reduces and then gradually becomes tension. So at one point, it's somewhere in the middle of the beam, there has to be one axis which is neither getting elongated nor compressed. So that is a neutral axis, and that is what this point here denotes. And when a section is fully plastic, the this part is in compression and this part entirely takes the Fy stress, and this part also take Fy stress, but there are two on other sides because this part is maybe compression and this part is tension. Then there is another failure in beam called local buckling. In this is only happens in steel beams, because in concrete structures, in concrete beams, the cross section is a constant thing. But in steel sections, we don't make solid rectangular or some or sections like that. We have sections like this. So you can see that the width of the section, like here it's wider, here the thickness of the web is really really thin. Like a common joist IS 200 has web thickness of 5.7 millimeters. It's very very thin. But in concrete structures, you have never made a section that thin. What are the general dimensions? 200 by 300 millimeter, or 600 millimeter, something like that. So these are much much thinner than the kinds of dimensions we are used to encountering in concrete structures. So local buckling is an issue here. During the bending process, if the compression flange or a part of the web is subjected to compression is too thin to take any appreciable amount of compression, then the plate may fail due to buckling even before the full plastic moment is reached. This means that the entire section has not failed yet. The entire section can still take the load and it won't actually fail completely, but you'll see a buckling in this zone, in a particular zone. This is the flange, and the flange is the horizontal thing of the eye, and the web is the vertical part. And similarly in channel also, the horizontal parts are called the flanges and the vertical parts are called the webs. So there is a local buckling in the flange, and even if the entire section probably can take the load, we don't want this to happen. We have to prevent this local buckling as well, because it makes this zone particularly vulnerable, and this zone may locally fail and then lead to a global failure eventually. Then there is shear that we are used to. Generally, in portions near to the support, very large shear exists. You know that from concrete structures as well. That shear is most critical at the supports, and bending is first for simply supported beams. The shear is most critical at the supports, and bending is most critical near the center. So generally, in portions near to the supports, very large shear exists. In this case, the beam may fail in shear if the web is not of sufficient thickness. Formation of plastic hinge accompanies this process, like shown here. This is the support, and this kind of shear is basically a diagonal force. Shear develops in such a way that the shear cracks are always diagonal. Bending cracks are vertical because the material is getting pulled or pushed in the horizontal direction. So the cracks develop in the perpendicular direction to which the force is being applied. And so here the shear forces develop in pairs in such a way that the resultant force acts in a diagonal direction. So the cracks appear in the perpendicular direction to that diagonal direction, which is also diagonal. So this is how the shear zone develops. And another thing is that why do they say that the beam may fail in shear if the web is not of sufficient thickness? That is because when we are designing a steel structure, for these common sections, the flanges calculation shows that calculation when we go to the calculations, you will see that the bending moment capacity of the flanges is much much higher than that of the web. Okay, because bending moment depends on BD cube. It depends on the cube of certain quantity that is very high in the flange because the width is high. So we can roughly say that we want the flanges to take the bending moment develop, and we want the web to withstand the shear. Similarly for this channel, we want these two flanges to withstand the bending moment and this web to take the shear. So if the so failure tends to happen when the web is not sufficiently thick, and bending failure tends to happen when the flange is not well designed enough. Then there is a shear buckling mode. Buckling during the shearing process, if the web is too thin, then it is prone to get failed by buckling, as shown here. These are see the cracks develop in a diagonal sense because the tension and compression develop in these two per cross directions. and there is another called web crushing and buckling. This is the term they use in codes. So web crushing and buckling is also a design criteria because high vertical stresses acts on support, and at location of load points, the beam web may fail by crushing or buckling. And these buckling is, you must have come across buckling somewhere. Buckling occurs due to compression. Buckling is not an issue in concrete. Again, it's not at all an issue in concrete structures because concrete structures are never that thin, and buckling happens in slender structures. If there is a slenderness ratio that probably you have done in your second year in solid mechanics or theory of elasticity, if you have learned, you will know that there is a slenderness ratio developed from Euler's beam theory, Euler's buckling theory. So this buckling is an issue. Buckling is an issue in webs in steel structures. In concrete is not important, and crushing is a failure in the beam in the flange web interface. And there is another lateral torsional buckling. So this is the 3D view of the I section. This is the section, and this is the beam. It is supposed to go like this. Lateral torsional buckling is like they rotate by separate different amounts, and it's basically a kind of torsion that leads to buckling. This type of failure occurs when the beam has high flexural stiffness in the vertical plane as compared to the horizontal plane. The beam has a tendency to deflect sideways. And for example, this is an example. This is a loaded cantilever. This is a bolted design. We won't go into the details right now because we haven't covered bolted connections or welded connections yet. And there's another called the common one, deflection, that is there in all structures or even in concrete structures. It is quite practical that a beam does not fail due to excessive deflection, but on the other hand, too much deflection can lead to discomfort to the occupants. Like if you see, if a resident sees that the ceiling is sagging, they will feel uncomfortable. They will feel that the structure is about to collapse, and that it may seem trivial, but it actually is not. Even if the ceiling does not collapse, if the residents feel that this building is not fit to be lived in, they will call repairmen, they will call civil engineers to take a look at this, and they will ask for repair. So that deflection is also an important criteria, not just if it actually hampers the movement like headroom and all. Excessive deflection can also cause discomfort. Now, why did we look at all these? All these modes: bending, local buckling, shear buckling, web crushing and buckling, lateral torsional buckling, and deflection. All these seven we looked at because these are the design criteria. So when we are designing a steel structure, so when we have to design a steel structure, maybe a particular beam or a column, we have to ensure that all these one, two, three, four, five, six, seven, all these seven criteria are satisfied. That is, the developed bending moment should not exceed the bending moment capacity of the beam, like that. All these of course you cannot just say what the local buckling is going to develop or what the local buckling capacity is just by looking at a structure. Like for concrete, we could still understand some things intuitively because they were rectangular sections, conventional rectangular sections. These are very different entities, and they are all given in the IS code. So, and there is physics behind it, but the physics is kind of new. So we have to look at all these design criteria when we actually go into the design. These are the components we need to know. Now we come to the loads. There is direct action. Now, loads are the forces that act on a structure, and loads are in fact the action on a structure due to which a structure responds. Right? The response of a structure is reaction, and loads are the action. And there are two types called direct action and indirect action. Direct action, these loads act directly on the structure and include dead loads, live loads, snow load, wind load. The intensity of these direct actions have been described by various codes and standard. Like in India, you know that IS 875 part 1 to 5, I'm sure you have seen, and IS 1893 is for earthquake loads. These are all direct loads. IS 875 part 1 is for dead load, part 2 is for live load, part 3 is for wind load, like that. And uh, these uh, these loads are common to whatever kind of structure you are building. The load doesn't tell you that take this much live load if it is a concrete structure and take this much live load if it is a if it is a steel structure. It is what you have to design a structure against. And indirect actions are sometimes loads act on the structure indirectly, like due to temperature change, settlement, deformation, etc. Where temperature change is important in steel structures because it has a high thermal expansion coefficient. Settlement means settlement of foundation. Suppose somewhere, do we saw what happened to Wayanad recently? The soil, what happens when there's a landslide, the soil settles. So that leads to the foundation tilting, and that leads to extra stresses developed on columns or on the entire structure. But it starts from the foundation and it gradually propagates to the entire structure. And deformations also, that if when you are designing a structure, you design its individual components. You design all the beams, all the columns, all the connections. But suppose one member is not designed well or something. If that member deforms, it will, someone has to take the stress. The structure as a whole has to take the stress unless it is to fail. So if one element does not take as much stress as we assumed it to take, the stress will be transferred to some other elements. So that also develops an extra indirect loads in the other sections. So these indirect loads also need to be taken into account in the design process. And reactions due to actions on a structure. As per limit state method of design, we will look at that now. The structure is required to satisfy the limit state of serviceability as well as the limit state of collapse, as I told you in the beginning. A structure needs to be assessed for the effects of design loads, including its individual members and connections. That is how we do it. We can't. A structure is made of its component, and we can't design the entire structure at one time. We have to go component wise. We have to we have to design each of the components. Then we have to design the connections. Then we can see how much, if the entire structure can take the load which we are expecting it to take. And this analysis is done either by using elastic or the plastic method of analysis, which we'll look at later. Now there are two methods of, because this is an overview of design of steel structures, that there are two design criteria. The various structural design requirement criteria relate to corresponding limit states. These the limit states are what we talked about earlier, the bending, local buckling, and so on. And thus the design of the structure is to comply with all the essential requirements that, and we will see what limit state design means. And there are two design criteria: the strength design criteria and the stiffness design criteria. These are related to, okay, maybe just for the in a very simple manner, we saw the stress strain curve. We saw that if you plot stress on the y axis and strain on the x axis, the stress strain curve goes in a vertically upward direction, and the slope is the Young's modulus. So basically, force or stress is the y-axis thing, the sigma that we denote by sigma, and the Young's modulus is the stiffness term here. So Young's modulus is stiffness in case of tension. Then there is a shear modulus, there is a bulk modulus. All those are stiffness terms. While stress is related to the 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 stress developed, the force you apply, force divided by area, and just like that. So strength and stiffness are very different things. They sometimes, I have known people to confuse between the two. I myself used to get confused between the two, but they are clearly different criteria. And just to visualize, you just think of that relation you have learned in childhood. Sigma stress is equal to Young's modulus into strain. So stress is the strength part of it, and the Young's modulus is the stiffness part of it. And the strength design criteria are related to possible modes of failure to a structure due to overloading and or under strength conditions. These design criteria are concerned with yielding, buckling, fatigue, brittle fracture, corrosion, the things that we learned earlier. All the criteria that we saw, except the deflection one. All the criteria that we saw here: bending, local buckling, shear buckling, web crushing and buckling, lateral torsional buckling, all of these are strength related criteria. Only the deflection is a stiffness related criteria. So the major design philosophies under these criteria are the working stress method, ultimate load method, and the limit state method. Now the working stress method used to be really popular initially, like when the Indian codes were written for the first time, and 1900s mostly, working stress method was very popular. Then the limit state design started coming around in the late 1900s, and now it is the most popular design method. And ultimate load method is not generally studied about. Working stress still you will see in some books or in some courses there is an introduction into the working stress method, because it used to be really common. Like my father is a civil engineer, and when he still works using the working stress method, because when he was a student he learned that method. So it is that recent, like 30-40 years ago it was in use, and the limit state method is currently in use. So we only learned the second one in details. And the stiffness design criteria, these design criteria are related to the serviceability of the structure under working loads, and they are mostly concerned with ensuring that the structure has sufficient stiffness that may otherwise lead to excessive deformations, including deflection, distortion, sagging. They all come under the bracket of deflections, while all these yielding, buckling, fatigue, brittle are all different things. Deflections, distortion, sagging, you can all put it under the same blanket of deformation, of deflection. So this is a brief look at the working stress method. The theory is based on the idea of computing the stresses and strains in the structure as a result of applied forces. This basically operates under the assumption, this is the assumption, that both concrete and steel display linearly elastic behavior, where the stresses are directly correlated with their corresponding strains, and the allowable stress values for concrete and steel are ascertained by considering the factor of safety. You may have already come across this during concrete design. The safety factor, that on loads see, we want a conservative design, right? We want a safe design. So suppose we think that a certain load D is going to come on a structure. If we want to make it safer, we will multiply D with the a factor of safety that is greater than 1, because we will assume a higher load and design it so that it definitely withstands the existing load. And similarly for capacity or strength, we will apply a factor of safety that is less than 1. We will assume a lesser strength than my structure actually has to make it safe. So there are the two factors of safety. The factors of safety acts as safeguard, accommodating the various uncertainty in material properties, construction techniques, and all these. So basically, uncertainty is a very important term. Uncertainty, we don't study about it a lot, but there is a huge area called structural reliability that studies about uncertainties, because we say that my steel, this steel section has an yield strength of 250 megapascal, but after all we can't actually guarantee 100% that it is correct. So we take a less than one factor of safety on material. And construction techniques, like there are so many factors that are variable when a structure is being constructed. The material can be wrong, the method of construction can be wrong, compacting, for concrete you have to compact the material and all, that cannot be carried out perfectly well. So these uncertainties we cannot control. So that is why we apply these factors of safety, that so that considering that, even if so that even if there are certain factors going against us, that is the material uh, that we are using is weaker than what we assumed, or the load that somehow it comes more or something, our structure will still be able to withstand it. Of course, again, reliability is how safe a structure is. We cannot take the reliability up to infinity, we have to draw the line somewhere. But these factors of safety actually account for the uncertainties. There are advantages. It is very simple. Basically, working stress method is simpler to understand than limit state method. It has been widely used for years, and most people, even the older engineers you will see, the site engineers you will see these days, the ones with experience are still working with the working stress method. So that actually in civil engineering, it's we don't actually work in offices. It's not the work that goes in the office that is important, it is the work that goes on in the site that is more important. So it actually matters what the people there know about more. The method is generally conservative in nature. It tends to result in safer designs by considering lower allowable stresses. But again, anything that is conservative is also most likely more costly, so it's less economical. It allows for easy comparison of the design with the permissible limits. By using this method, engineers can achieve economic designs by optimizing the use of materials, this is actually this can be done with limited design as well. The work with stress method can be easily integrated with IS codes and standards. It is particularly suitable for designing simple and common structural elements like beams, columns, and slabs in concrete design particularly. And the analysis required for this method is often complex, is less complex than other advanced methods, making feasible for smaller projects. It's a faster method basically. And the disadvantages are the method doesn't fully consider the elastic behavior of materials. This what this means is basically it assumes the working stress method assumes that the yield stress of a material is its ultimate strength. So yield strength if you consider the yield strength as ultimate strength, it is not actually the ultimate strength. Even after yielding, it can take some load, right? So if you put a barrier earlier, it underestimates the strength, right? And then it makes the structure uneconomical in the long run. While over designed structures means that you're making it conservative, you're making it safer, but you are also using more material and thus increasing the construction cost. This method is the reliance on allowable stress makes it sensitive to variations in material properties that may lead to inconsistencies in design. It is unsuitable for complex structures and situations involving non-linear behavior, dynamic loads, or unique loading conditions. These are very specific cases, and the working stress method is a very simplified framework made. So it is okay for simple structures, but for complex structures, it is better not to go for it. And depending solely on allowable stress limits might not provide adequate safety margins for modern construction practices. It doesn't consider the redistribution of stresses after structure yields. Again, this is what happens, that it just works that the none of the material is going to yield at all. The yield strength is what we consider the maximum one, and we don't when we are designing, we don't let the structure actually reach its maximum stress. So it doesn't go up to yield. It's as if the structure is non-existent after it yields. So the redistribution of stresses is also not accounted for in this method. And the method might not effectively account for the properties of advanced material that exhibit nonlinear behavior, such as fiber reinforced composites. And the method also doesn't consider time dependent effects like creep and shrinkage, which can impact long term structural performance. Now, the limited method. This considers all the relevant conditions pertaining to limit states of strength and serviceability. The strength limit states are based on load carrying capacity of the structure, which includes buckling, fatigue, fracture, the ones we looked at. Serviceability limit states are based on performance of the structure under actual application of service load. It includes vibration, deflection, corrosion, etc. The loads at working conditions are factored by the use of partial safety factor for loads, resulting in factored loads or design loads. Okay, in the working stress method, we don't apply a safety factor on the load. Okay, in the working stress method, we only apply on the capacity. Here we apply on both. On the load, we apply a safety factor greater than one, and on the capacity, we apply a safety factor lesser than one. The normal strength of the material is called its ultimate capacity, and the corresponding design strength of the material is obtained by dividing the ultimate capacity with the partial safety factor. So why do we divide it? Because we want to go for a conservative design. So if the actual ultimate capacity is 400, we would assume maybe it's 370 or something, because we will allow it only up to 370. So that means that even if something goes wrong, something is uncertain, it might exceed 370, but it won't exceed 400. And the member is designed so that the basic criteria is the design action should be less than the design strength. What is the design action? It is the load multiplied with the safety factor, and the design strength is the strength divided by the safety factor. Advantages of limit state design. This method recognizes that design parameters are variant. This method logically deals with the fact that there exists always a possibility of variations in loads and material properties both. And this method gives different weightage to different loads and materials. So there are load partial safety factor combinations given in the IS codes. Like we apply some 1.5 on live load because it's more variable. I think we apply 1.2 on dead loads. Yes, it's something the matter. Yes, Arman, you want to say anything? Okay. See, the method recognizes that design parameters are variance. This means that the reliability that I talked about, reliability, the area deals with uncertainties of parameters. Okay, so when we are, like I said before, we we are saying that this steel section has an yield strength of 250 megapascal and an ultimate stress capacity of 410 megapascal. That this how we are saying, we have we know this from certain lab tests that this is going to be the material properties. But when we are actually designing it, when we are actually manufacturing the material in the factory, all the factors, we cannot keep all the factors constant, that every steel section that is manufactured has the same properties. So some will have greater yield strength than 250, some will have lesser than 250, and we don't know what it is. We cannot test every individual material, right? We cannot test it for its yield strength or its ultimate strength. So we know an average value 250 is the mean value that we take, and then we accommodate some kind of variation, maybe 10%. If you have learned statistics, you will know that any the parameter can be defined by its mean and its standard deviation. So the mean is 250 MPa here, and maybe there is a variation of 10%, like 20 plus minus 25 MPa, idhar udhar it can happen. So that is why we apply this safety factor, the safety factor on the strength, that to suppose if on 250 we are applying a safety factor of 1.1, that is we are dividing it. So the 250 by 1 divided by 1.1 is something like 235 maybe, and that is what we are going to consider for the design. You realize that that makes the design safer, because we are assuming that the structure is weaker than it actually is. So in my design I will only allow the stress to develop up to 235, so that even if that section was weaker, like we know that in an ideal case the section will have yield strength to 250, but we don't allow the stress in it to develop more than 235. 235 is just a representative value I'm using. 235 is basically the 250 divided by the safety factor. We don't let the stress develop uh, exceed 235, because the situation is not ideal, and the section may actually have a lesser strength than 250. Again, we cannot allow it, like we are allowing up to 235. We could also allow it up to 200. We could take a very high safety factor, we could divide it by 2. Suppose 250 by 2 is 125, so we could also say that we will take a safety factor of 2. But then the design will become very unconservative. It will become very conservative, and it will become very uh, uneconomical. And then design parameters, strength are not the only design parameter, the loads are also design parameters. So the loads, we are assuming something. We have in IS code, there are some norms that in residential buildings you have to take 2 kilonewton per meter square live load. But still we will apply a safety factor on this, maybe 1.5, and we will design the structure not for 2 kilonewton per meter square, but for 1.5 into 2 kilonewton per meter square, so that in case there is an extra loading someday, in case something goes wrong and the load is more than what we are expecting, the structure doesn't collapse. But again, we cannot design it for 10 kilonewton per meter square, then the structure will become very uneconomical. So basically, limited design, by putting a safety factor on the load uh, and on the capacity, it recognizes it accepts that there can be uncertainties, and we are dealing with that in a simplified way of just multiplying or dividing by partial safety factors. Now how these partial safety factors come has to do with the area of structural reliability. We decide that we want this much safety of the structure, and from there are methods to decide upon what the safety factors will be. As we vary the safety factors, the reliability of the structure increases or decreases. And as I keep saying, my MTech thesis was on structural reliability, so I know a lot about this area. And there is always the bottom line is we have to draw a line between reliability and between safety and economy. We cannot make it keep on making it safer and safer, but again we have to, but we cannot also make it more economical and more economical, and end up making it very unsafe. So these standards are also decided by our codes and by researchers. Basically, researchers set these standards, and they simplify it in the form of partial safety factors that anyone can use from the code. I hope it's clear now. And now this method gives different weightage to different loads and materials as well, like different kinds of loads. For example, in Dead loads, we give a safety factor of 1.1, I think, 1.2 on dead loads, 1.5 on live load. What does this imply? This implies that we are expecting more variation in the live load, so we are putting a higher safety factor on it. And dead load is more or less, we can predict it better than live load, at least because it is a self weight and floor finish which we can pre-calculate. But live load is something that, like the vehicular load in a bridge, you have assumed a certain live load, but there can be an extreme traffic situation someday that too many trucks are passing on the bridge at the same time or standing on the bridge at the same time. So we have to allow for some variations that is possible. And the disadvantage is there is a likelihood of design errors because of more complex theory which are not so in the working stress method of design. So this is a more complicated method, and limit state method of design is far better than other design philosophies. I don't know why this is a disadvantage, but yeah. And IS 800-207 is a design code for structures which is based on limit state method of design. However, it still maintains the working stress design approach. So this 2007 stands for its last revision year. So it was last revised in 2007. Before that, I think it was in 1980 or something, which my father or anyone who studied in those days used. That had majorly the entire code was based on working stress method approach. But then it was revised in 2007, and now it mostly incorporates the limit state method. You will see some section, some appendix or something that maintains the working stress design approach. Both, and no, you can't say this is right, this is wrong. It just depends on what you want to do, and both are supposed to give you safe enough results. And design load and design strength, we'll look at these two topics last today. The design load in limit state method of design is obtained by multiplying the working load with a partial safety factor, and the resulting load is called the factored load or the design load. Different design loads, that is depth load, live load, wind load, earthquake load, are then combined under the most severe but realistic conditions. Again, these combinations are used, like we don't use it for the worst combinations. Like, see, a structure has 1.5, suppose structure and the gravity loads are dead load and live load. And dead load, we generally apply a safety factor of 1.2 on dead load and 1.5 on live load. But when we there is a load combination called dead load plus live load, because they are acting in the same direction, right? But we don't add 1.2 dead load plus 1.5 live load. There are certain combinations that are also stipulated in the codes, which I'm sure you have studied in RC design if you have taken that course, which you should have taken before design of steel structures actually, because RC design, it goes more basic, and the design of steel structures, the course assumes that you know certain things about design, and so different design loads are then combined. So the loads, the safety factors, and the load combinations are all shown in the code. And the design strength of the material is obtained by dividing the characteristic strength of the material by a suitable partial safety factor. Again, I told you why this is divided and this is multiplying. This is because to make it safe further than to make it unsafe. The design strength of each material and their connections must be such that the most severe combination of design loads must not cause failure. So basically, the most severe design load and the weakest design strength, they should, like, the strength should be more than the load. The bottom line of design is this: the strength of the structure should be more than the load it withstands, because then it will not fail, right? If the load exceeds the strength, it will fail. So the design strength of each material and the connections must be such that the most severe combination of design loads must not cause failure, and it must also be ensured that the structure is stable against overturning, sway, etc. These are some extra criteria that it's mostly that if we design in the normal course, these criteria are already satisfied, but there are many aspects, like deflection is one aspect, overturning, stability is another aspect, not so important in design of steel structure, or at least in this course. So, okay then. If there are any questions, next class we'll look at bolted connections. Now that we have had a basic look at the material and at the design philosophy, next class we'll start with the actual design and we'll start with connections, which is very important in steel structures and not that important, not at all important in concrete structures, because the entire structure is cast together: beams, columns, slabs, foundation, everything is cast in an integrated manner. But in steel design, the sections that I have shown you, the sections come in that form only from the factories, and we have to connect them. The beams and the columns and the multiple beams, they are all separate entities, and you have to connect them. And so the connections are two types mostly: bolts and welds. And the connections are also have been studied to be one of the weakest links of a structure. So in a steel structure, so if a steel structure fails, it most often fails when the connection fails. So it's a topic of great detail we study. We'll start with bolted connections next week, and then we'll move on to welded connections. Arman, do you have any other question? Your hand is raised. Okay, okay. Anyone else has a question? All right, then we'll meet next Tuesday and study bolted connections.